Okay. First of all, I would like to congratulate everybody with your excellent win, which just happened, and India defeat Pakistan. So my great congratulations to everybody. It's a very happy moment, and I'm happy that I'm here at this year happy moment. So my congratulations, big congratulations to you. Okay, so today we have the following plan, which is shown here, but I very slightly change it because actually, as far as I understand, there is not so good understanding how this global flow is working. So I just briefly repeat you, just in order that you can understand this previous part, and then we proceed more complicated shear layer structure part. So actually, we define the flow near the Ekman boundary layer via the three free functions. So you see that here we have, where is my mouse? Oh, this mouse. Here you see that velocity field, which we are looking for, is defined in terms of three somewhat function which should be identified. First function is the function which is directed along the latitude, and this one is the unit vector in latitudinal direction, and it's actually depend on the latitude itself, and also of course there is dependence on the stretched variable which we discussed previously. Hopefully you understand it well. And this stretched variable is constructed in the way that it catch the boundary condition. Exactly at the boundary condition, it's just change in the way that to satisfy this boundary condition. But outside the boundary, this stretched variable make the contribution from the boundary conditional structure negligible, or already if we just not so much from the boundary layer, then we already have no boundary layer structure, and we should tune on the geostrophic flow. So especially geostrophic flow could be represented like that. Here r sine theta is the cylindrical radius, but represented in spherical coordinate. And so also, of course, should be the similar function, some free function, which we here show by small u. Here there is capital U for geostrophic flow, and this one is for the small u. And also, of course, now it has a component which is due to azimuthal component. This is unit vector in azimuthal direction. It's necessary to stress out that this Ekman layer, Ekman boundary layer stuff is somehow independent, not somehow, but exactly independent on the azimuthal component phi. But nevertheless, of course, it could have the component of the vector in this direction, but it's not dependent on it. It's important to understand because of the symmetry of the problem. So eventually we reduce the all this problem to the problem for this stretched variable, and we get such a simple equation, which in fact the equation of which depend on two functions, sort of free function, which one is small u and another is v theta. And so it's rather simple equation. It has and boundary condition is here is shown, to which we are tending. One boundary condition is near the outer boundary here. I just remind you that for the case of the Earth, it's about 3 non-dimensional units. And another boundary condition is on the inner boundary. And there is imposed differential rotation. So this imposed differential rotation represented like that. And so eventually we have all the boundary conditions we should satisfy. And as I already told you, we should represent this variable, stretchable variable in the exponential form. This is the best and natural form because it's come out from the solution of this equation which I previously showed to you. And so it's somehow show that actually this exponent, when theta is not, then it's satisfied to the boundary condition. When it's not, it's going away from the boundary, and depend on the which boundary we going away. We put different signs here, which follow from characteristic equation. And eventually we also can solve this, can write down characteristic number which appears from this equation. And this lambda is equal, shown here. So in the end of this story, we combine everything. To this maybe lengthy formula, but it has very clear meaning, because actually this is theta component of the velocity, and from this equation we can get another component of the velocity. For example, from this we can find u using this theta component from here in the last equation. So actually, in formal way, the whole solution is determinate. I hope that at this step is everything much more clear. I repeat it, but not on the blackboard in a very detail, but the essence of this, in hope that you now understand how this is working. So let's proceed now to the geostrophic flow itself, which is again, yeah, I will repeat for your better understanding. Okay. You see that we constructed the function in my previous talk. We've constructed the function in the way that the contribution from geostrophic flow and this free function is equal 0, just in order to satisfy boundary condition. And also we constructed on another boundary. Here the subscript O means that we construct on one boundary, while subscript I means that we were doing that on another boundary. But anyhow, at which boundary we are doing it independently, eventually all these values are dependent only on cylindrical radius. And here you see that we have 1, 2, and also there is a small u function which is not mentioned here, but nevertheless, okay, we have 3 actually. Here we have 3 functions, but there are only 2 equations. So to find the third equation, to match the number of the function and the number of equation, to successfully to resolve it, we are using divergence condition, but integral form. So we just here you have a picture how it's everything is shown, and in this picture you see that if we make special notation for the z coordinate on the inner boundary, this z coordinate on the inner boundary, this one you see, I pointed out it by mouse. So we can integrate inside the tangent cylinder from this boundary in z direction up to the upper boundary. So we and this integral is equal 0 because it's the natural consequences of the divergence-free equation. So then we split this integral. You see that the most valuable part of this integral is directly near the boundaries, here and here. So we can split this integral on 2 component. So here I wrote that it's approximate, but approximation is very good. As far as you remember, for example, for the case of the Earth, even if we consider turbulent situation, the square root of Ekman number is 10 to minus 4. But if we go to molecular situation, it's even better. So we can consider the boundary, not all this space from the inner boundary to the outer boundary, but we consider just small tiny part here and tiny part here, and we can quite actually almost exactly to represent this integral only in this small parts of all the parts, just because all this final function, which is exponentially dependent, they are vanishing well outside the boundary layer. So eventually we get, after some manipulation, quite obvious expansion in small values, we get very simple result. Here the result is shown for the inner boundary layer. Of course, the similar result is for the outer boundary layer. Here delta I is the small contribution or small value of our distance for which we are going out of the boundary layer. And this distance could be of order 10, if you consider the Earth situation, it could be 10 to minus 4 again. Just few of that type, and it will be already enough. If we move only the square root of Ekman number, then we diminish this effect by the exponent. But if we go just maybe 2 or 3 exponent, we already diminish it dramatically. In many cases, it will work. So finally, here there is how it's working in the final form. When we substitute all the variable which is required, and eventually we see that this equate to this form. Of course, this delta I and delta O is vanishing. So here delta O, yeah, delta Y I saw on the previous slide, and delta O vanishing. So after all this integral and applying, so the final result of application of this integral looks quite simple. It's shown on this formula. So now we have 3 formulas and 3 variables. Of course, we can solve them. And perhaps the most interesting solution is for the geostrophic flow itself. More precisely for us, it's important to have the ratio of geostrophic flow velocity over the cylindrical radius, which is actually radial rotational rate. And this is shown here. In terms of the C, is I just remind you, C is the ratio of outer boundary to the inner boundary. So in the case of the Earth, it's about 3. In other planets and moons, it could be take its value, correspondent value. Then, of course, we have cylindrical radius S, and it's everything. And also it's matched to the YO function, which also, again, sort of similar to geostrophic flow. And here we have angular rotational rate. And in the similar fashion, we are finding this YI function in the inner layer. This is in the outer layer. This is in the inner layer. And so the resulting, the most important result of all this calculation is just to understand how this differential flow is working. And you see that we put this result here. I keep losing the mouse. And it's quite simple. You see that it's just monotonical function which starts from the half. I mean, not just trophic flow itself, capital U, but the rate of the rotation, which related to this geostrophic flow, because it depends only on cylindrical radius. And you see that it started from the half, then it's monotonically change it the way. Of course, this changing is dependent on this C, on this C, the ratio of the outer to the inner boundary. But in any case, here it's shown for the case of the Earth when it's about 3. Of course, there is some exact value. And so you see that here the peculiarity of this stream is that here it's quite smooth near the 0. And then the derivative of it is rising, rising, rising. And here it's become infinite. It's become infinite here at the point where the inner co-boundary ends, and this is point where there is the angular rotational rate, which is opposite rotational rate from the inner core. So you see that in this term, angular rotational rate after radius which exceeds radius of the inner core, it's just rigid body rotation. So it was not shown here, but nevertheless, here we have just line. And this just line is, of course, correspond to the rigid body rotation in this situation. And of course, it's physically impossible that we have such a huge jump in derivatives, and even more jump in the second derivatives and the third, and so on. So we should somehow resolve this. And perhaps it's the most difficult and interesting problem which was done finally by Stewardson. And then I proceed further to this. But at the moment, I would like to make sure that you understand this relatively simple part, and maybe there is some question remains. Or you understand everything now. Is there any question, or you understand? Please, somebody say that he understands. Is it clear? Is anybody who clear? Or nobody? Huh? Yes. There is one. Okay. Thank you. Okay, let's now proceed to the third. I already spent some time on explaining this first layer structure, but nevertheless, let me just remind you what we have done. Okay, so in our case, I just remind you what we have done already in detail, but for your better understanding, let's now remind this stuff a little bit in some general detail. The general thing is that show the better structure because I showed the equation. In general things, we presume that here you see the picture of this problem. You see here there is the liquid core, there is the rigid core, and there is also just rocket flow, which is inside some
similar. In this Asymptotic flow is actually what clear. I hope at least for some of the people is clear. So now we proceed to the so-called Stevenson layer, which is here, which is located here. And if you got the picture, now we will try to understand how this layer is working. And the first thing to do is to write down the system of equation. And for writing down the system of the equation, we should have in mind that in direction perpendicular to the shear layer, there is the most valuable variable. For example, here you have 4 equations, and in this 4 equation, we mainly using that the Coriolis force is dominated, that the geostrophic flow is dominated, and the derivatives against the cylindrical radius, like here, 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 and here, these derivatives against the cylindrical radius is the most important, while other terms could be neglected. So this is the major system of the equation, which by identical transformation would be reduced to the equation just for the pressure and for the velocity in this direction. And so actually these two remaining equations are actually consequences of these two equations. So we just can at the moment forget about these two other components of the velocity. But we can explore the velocity, which is velocity and pressure, velocity in the axis, in the direction of the axis of rotation of the and again we're using pressure. So then we should understand in which power of Ekman number all the stuff is working. First of all, of course, we scale somehow the distance from the cylindrical radius. And this distance from the cylindrical radius is some power, inverse power of Ekman number, which we denote by beta. And then we should cover balance in both of these equations. And if we scale the pressure as somewhat smaller part of the velocity in the direction of the axis of rotation, and we make this scale as alpha, so perfect balance between these two terms in this equation and two terms in this equation, it's required this simple linear system which consists alpha is equal to 1 minus 2 beta. So you see that alpha is coming from this term, 2 beta is coming from this term, and of course it's we should subscribe this 2 beta. And if we consider another equation, you see that there is Ekman number in the first power here, and here we have 4. For the 4 in the power of beta, so there is 4 beta, and also because we have the pressure here, this pressure is as we scale here, we maintain this alpha contribution. So eventually, this is a simple linear system, and it has a simple solution that the thickness of the layer and the ratio of pressure to the velocity in this direction is typically regulated by the power law 1/3 here and 1/3 here. And I just want to remind you,
stress it, that this is the e to the 1/3 layer is the most important layer, and it's lie down in the very middle of the shear of all the shear. There are some less important layers which are nested around this layer and in the equatorial domain. We will proceed to them later. Okay, so now it's important to understand how this solution is working. So up to this point, yeah, I am repeating. So, but here maybe it's now time to proceed with formula. Okay. Okay, now we should repeat the formula. There is quite general approach which allow to solve such a problem, similar problem. And here you have what is written in the on the PowerPoint slide you see, but let us rewrite it once more and just to explain how all this stuff is working. So we have, as already told, we have z component of the velocity. Also we have pressure. And actually it's enough these two functions to define everything. And it's equal, in our case, exponent to the power square root to the power of s function, very important function because it's also depend on small s, which is cylindrical radius, and it's a singular function. Why it's s? Because it's a singular function, and it's actually divided by. Okay, let's write it slightly another way. Oh no, not so. Yes. It's necessary to stress that it's third root of Ekman number. I write it in another fashion. Because you see that this is go in denominator. So it rises very dramatically, this value. So when this thing is acting against this shear layer, we have the dramatic effect on the change of it. Okay, of course, it should be such an effect because actually we are looking for the solution which adjusts with almost infinite value. So, but the rest is in regular form. It's interesting to see some interaction. In Sunday, Professor Rameshwar spoke with you with regular and irregular representation. So, and singular and regular representation. Here we have both in one, because there is a singular part, this one. And there is also regular part, which is working in quite a regular way. We just take square root of Ekman number, multiplied it on n. This is our small parameter. And at each n, and n is starting from 0 till infinity in principle. However, in such sort of the approximation, because we have very strong singular function, it's no need to go to larger n. Usually, even 0 order is enough in some cases. But maybe first order or second order is already give a good approximation. So, and this is on this depends again on vector, and this vector could be written like that. This is z function of n. They also the function of cylindrical radius. And then there is a square root of order 3 of Ekman number, which multiplied it on the pressure. And pressure is also N. Okay. And so let's now proceed. This is formula 3b2. You already, as far as to my recollection, you already write it down. Here you just have it in slightly different form, maybe for your better understanding. But it's of course the same which we wrote before, but maybe in slightly different rotation. So substituting this function to this equation 1. So we have two equations, as I already told to you, and we substitute this function to this equation. So, and eventually we are getting the result, which I will write here and comment. So, first of all, of course, we are considered the zero order. And as already told, with such a good accuracy of this approximation, in fact, for the general purposes, it's more than enough. The zero order is enough. Maybe if somebody want to have some details, you can go to the first order. And by the way, there is an interesting question, because actually all this Stewardson layer structure and so on was found 60 years ago, something like that, 66, almost 60 years ago. And it was no computer there at that time, at least so powerful as it now. And it's interesting thing that, to my recollection, nobody showed on the computer how these fluids look like, only in formulas. They only obtained the formulas, but how it look like inside this flow. Maybe there is, I'm missing something, but it could be interesting to do such a work, just imitate in the this Stewardson layer and so on, and to understand. Okay, it's just a dream. Maybe not a dream, of course. Maybe somebody will do it, and it will be very good illustrative example. But nevertheless, let's proceed to the system. And this is partial derivatives of PO. Oh. Okay, I will just keep you, for your understanding, I will keep the initial system. You see, of course, we are first applying to the first equation. And so we have dp naught on dz. And it's simply equal. Oh, why it's finished. It's simply equal. It's necessary at this point to stress out that it depends directly on cylindrical radius, while this depends only on cylindrical radius, while these two could depend not only on cylindrical radius, but they also could depend on the z in the direction of the axis of rotation. So here we have this. You see that there is also the derivatives in z direction, not only in s like for this single function. And this function is going here. Maybe it's a major contribution. We just take the derivatives in z direction and put it in square. And here we have zero order of this z function, which represents z component of the velocity. So we write down the first equation. Let's write down the second equation. And this second equation look like PO over 4. And here there is a force power. And this simply equal dz O over dz. And we can get further simplification just from these two equations. We are getting, I show it like that, equation for the pressure only. Is equal. Here the 6th power coming first. And also there is contribution here. Okay, this is formula 3b3. And it's important that for this value we have general solution for this equation, and it could be represented. Okay. And this could be represented as it's written here, but I just repeat it and explain. So we have PO, this solution, some free constant, then cosine of S prime. Just to make these things shorter, we will denote by S prime the derivatives of S in cylindrical radius. Of course, there is only one value which is determinant, so it's easy to understand that this is ds by ds capital by ds small. So we have third power of this stuff. Then we have z over 2, and bracket is closed. And then there is a sinusoidal part, d. Okay, the similar expression, sine cubed z over 2. Okay. Okay. And this is the formula 3b4. And just to remind you that S prime is simply derivative of capital S over the small s. Okay. Here the prime denotes the derivative with respect to S, and C and B are constants that must be determined from the boundary condition on a rigid sphere. In this case, we can limit ourselves to considering only the upper hemisphere. Upper hemisphere, let me show you a picture. So here we can just restrict ourselves because of the symmetry of the problem. We only consider the upper hemisphere, this region I show you, or even more precisely this region. So we have a quarter of the whole sphere, and it's more than enough, because actually it already has the symmetry against all this stuff. So actually we consider only this slice. If we consider the like an watermelon, so we can take this slice, fourth part of it, and it's enough to consider it here. So and the remaining part we can get just because of the symmetry. And boundary condition. In this case, we can limit ourselves to constructing only upper hemisphere z equal more than 0. So let's write it down. Z zero, and discard the second term in 4 because of this symmetry. So we can just discard the second term in 4. This second term, this one. Due to the symmetry condition. So we can suppose to satisfy this symmetry that D is equal naught. So because there is obvious equatorial symmetry of the problem in respect to the equator, why I said you that it's possible to have this a quarter size slice. So here we can neglect this. So it simplify somehow. Let us first consider the region as greater than 1. Oh, sorry. Okay, I'll put it. Is it seen? O equals 0. But actually this condition is always we are looking for. But another temporary condition first we consider is that S is greater or equal 1. So the outer part of this boundary layer, no, not boundary layer, sorry, shear layer, outer part of this shear layer, which is on the way to the outer boundary. Okay, here it is easier to set the boundary condition since outside the shear layer this entire region rotates like a rigid body. And in this case, at z equals naught, it is sufficient to satisfy the symmetry condition in the region which we have already done. We already done this symmetry condition because if you remember, I showed you the strophic flow. There is, of course, obvious equatorial symmetry condition. The remaining boundary condition in the upper part of tangent cylinder, see here in the upper part of the tangent cylinder, there is actually boundary condition here outside on all this part, but also there is boundary condition here on the upper part for this shear layer. The remaining boundary condition in the upper part of tangent cylinder near the okay. Near that equal that all here I've just remind you our previous stuff when we end from 1. That O from 1, it's exactly on the boundary and it's equal I just remind you, we already used this notation, but now there is just remaining. So at this point, it's exactly the point which was on the top of this shear layer boundary, must be set taking into account the presence of the Ekman layer here, which is obviously thinner than any shear layer. So as I already told you, let's again go to the picture for better understanding. We consider now this layer, and this intermediate layer should be definitely should be thinner than any shear layer. So accordingly, we must consider the condition on the flow immediately upon exciting the outer Ekman layer. So immediately as we exciting outer Ekman layer, this one, or this one, oh, okay, it's another slide, so it's from this one. So here the vertical component of the velocity described in formula 3, this formula 3, by the function z naught, z naught, by the function z naught, this function. Must vanish since here the radial and latitudinal component of velocity are actually zeroed in accordance with, okay, from the formulation of our previous chapter, just because non-penetration condition. In such boundary condition can only be satisfied only when we have the condition, let's write it down. This here. So this boundary condition should be satisfied at the condition dp O over the z. Let's write it slightly in another form. At the point z equals z O, and it's just equal 0 at this boundary. And it's actually identically the same, like consider this singular function. And this for this singular function we have such an expansion as prime. So I remind you that it's derivatives, cylindrical derivatives. And here we have cube. And here we have remaining of the z I, c squared minus 1. Everything is divided on 2. And it's interesting to note here that this result is working in the case when this things becomes represented via the natural number and pi. So this is sort of the periodicity. Here n is a natural number. Accordingly, the general solution is constructed from the linear combination of components decreasing with the distance from the layer. Okay, seems we. Okay, so we almost about finished with this part. No, not finished, yeah. In a similar manner, but with adequately boundary condition at z equals naught. So here we are working at z equal zo, but also we could work at z equals naught. A solution is sought in the interior of S smaller than 1. So similarly, we can do the same exercises for S smaller than 1, so inside the tangent cylinder. Then both solutions are matching together at S equal naught to ensure continuity of the overall solution. So these two conditions are matching not Pakistani and English, Pakistani and Indian match, but just match. Matched together. So in a similar way, the quad boundary condition solution is thought in the interior S smaller than 1, part of this principal shear layer. Then both solutions are matching together at S equal naught to ensure continuity of the overall system. So also we have a S equal naught. At S equal naught. With the given in formula 2 up to 5, okay, I forget to number, sorry. This is formula 5, yeah. With the given 2, 3, 4, and 5 ratio between the velocities, it is impossible to completely remove the singularity in the differential rotation velocity, which we show in the previous slide. From the previous chapter we discussed, and this jump of the derivatives in the velocity. Therefore, an additional external shear layer is required. In this layer, only the terms of second equation 1 are completely balanced. Second equation 1, let's go back to this equation 1. Here you see that there is first equation 1, and here to consider this additional shear layer, we actually previously we paid attention only to this equation, or both of them more precisely. But in the reduced part, of course, to satisfy this additional boundary layer, we should use only this equation. So in this layer, only the terms of the second equation are completely balanced, and the first equation here, this first equation, just reduced to the most simple one, tremendously simple one, and this is just, oh, sorry. dp by dz is equal naught at this matching. And actually this is a geostrophic condition, and it's satisfied through matching with the main shear layer at the thickness e to the 1/3. Since the main purpose of the outer shear layer is to smooth out differential rotation, when in the third equation v phi, is of order actually e to the 0 or of order 1. In this case, reverse flow can also be realized in the same layer. Since the thickness of the Ekman boundary layer is Ekman boundary layer. Ekman boundary layer is of what the square root of the Ekman number. Then if we assume that the reverse flow is along the axis of rotation and Vz is proportional to the some power of alpha, please don't mistake this alpha with the previous alpha I used when constitute this flow. It's another flow, and it is another alpha, and it's locally for this local shell. So then from the flow continuity condition we have that this, okay, I'll write on top, this e to the 1/2 is subdivided on two parts, e alpha and e beta, where beta is now the thickness of the outer shear layer. Finally, in the outer shear layers from this flow continuity condition and from the last two equation 0, we obtain from last two equation 0 equation, this equation, last two equation 0, the very last which are on the bottom. Okay, we have all this condition listed here. Here. So just to put them into the equation and equating the corresponding term in order to have the balance, we have the following relation. Finally, in the outer shear layer from this flow continuity condition and from the last two equations of 0, these two I already showed you to you, you have the following relation. Again, the linear system. 1/2 is equal alpha plus beta and also there is 1 minus 3b equals alpha. So this is the system. And the consequences of this system is rather simple, that alpha is equal to beta and equal 1/4. In both of the considered shear layers, it is possible to smooth out the singularity of the differential rotation velocity for 6. It's in the previous chapter. Okay. Let's hope that you find it if you like. To ensure the return flow of the fluid and even to ensure the continuity of the second derivative of the velocity. So to ensure these two things, however, the first derivatives of the azimuthal velocity remains discontinuous. Therefore, a third sublayer, which is internal with respect to the main sublayer, is proportional to the third sublayer, which is in respect to E third, and it finally has the thickness. It's also could be called the thickness of this innermost sublayer is E to 7. Okay, it's from the similar configuration. Okay, I'll finish this chapter. Let me just show in picture how all this result is working. So we have the intermediate layer of order E2 1/3. Then there is innermost layer, which we just discussed, of E2 2/7. And also there is outermost, if you like, layer with order E to the 1/4. So, okay, so we just finished this paragraph, and I will be happy to answer your question. Okay. Is there any question?
The corner of the board, e to the power half equal to e to the alpha. This one. Left corner. Left corner.
E if one ruler to the power 1/2 equals to e to the power
How much steps?
alpha beta.
Sorry, what's this question? Please show what you want. This equation comes from the condition that the boundary layer of Beckman boundary layer is fit to the continuity condition, and the condition I forget which is what, but one of them is continuity condition, and another of them is the
Divide on corresponding cylindrical radius. Something like that. Okay, sure. Let me check. I don't remember exactly. So actually, this is coming from the. Okay. This one came from the this equation and continuity condition. These two, as far as I can recollect. Yeah. And is there any more question?
Sir, what about the 3B.3? 3B.3, yeah, how it came?
How many?
How it came, the 3B.3.
3B.
That dou P naught by dou Z equal to ds by ds the whole square. Yeah.
Okay.
Equation 3B.3.
3B.3.
Yes, sir.
Actually, we substitute this representation. We substitute to the equation, and so first result is that we are getting these two equations. Then we just use one equation for Z from here. We represent Z from here via the pressure and put here. Here we just make this equation. So we represent ZO from this formula, just equate ZO to dP by dz over this stuff, and then put this Z to this place. And it's then work like that. As far as I could see. So it appears like second derivatives, because here you see first derivative, and then you act another derivative. So this second derivative appear and remain from this. So it works like that. From this two.
But initially, how it came that dou P naught by dou Z equal to ds by ds the whole square of Z naught? The first one.
The first step how it will go, it's from this equation. This is the initial system. So we just represent, for example, again, we just represent some of the values. For example, here we can represent in the upper formula V phi via the P. Then we put this V phi via the P to this formula. And then we take, I don't remember exactly, but after that we can represent Vs and put it's again V phi already will be there. So we put Vs and put in this formula. And finally, we are in business that we obtain this two formula for P and Vz. And the remaining component of the velocity can be expressed via the P. So something like that. You can train yourself on this stuff.
Thank you, sir.
Not at all. Okay, so maybe we will have short break. Short or not short, I don't know.
Short break, after break we go.
So now we will be. Okay, let's proceed further. And actually, if we refer to this picture, we already outlined it. Of course, we didn't present exact solution for all these cases, but we made the qualitative analysis and on some place the formula analysis. So we have now all the formula to estimate all this shear layer, and we in fact investigated this shear layer, the most important maybe to say, which is actually has a thickness e to the 1/3. Then we investigated innermost shear layer, which is has a thickness this one of e to 2/7, and then we investigated outermost inner layer, shear layer, sorry, e to the 1/4. So of course, to get all this various layer, we balance it with the Ekman layer here and here. But there is another boundary to which this Ekman layer is balanced. This boundary is here near the equator. It's special layer here, which is shown here like this bump, and also there is a dimensional values for this layer. So, and we should not simply presume them, but we should prove that it's exactly the same relation for this layer, and we have to outline the role of this layer. It's actually the last, but not the least, of course, layer in this system. Perhaps it's even one of the most important. So let's start now considering this layer. So near the inner equator of near the inner equator of a slightly faster rotating rigid sphere, the condition under which the solution in the Ekman boundary layer were obtained are not satisfied. Let's go to corresponding presentation. Okay, it's here. Are not satisfied. This is due to the fact that the Coriolis force controlling this layer is of order cosine theta. Okay, let me remove. So now we are investigating quite another shear layer. More precisely to say, it's not shear layer. It's some combination of the shear layer and boundary layer. And maybe more, in some sense, it's even more boundary layer than shear layer. Of course, it has the traces of shear, but nevertheless, this layer is sort of boundary layer. While this layer appears, now I will write down to you, but the physical essence is that the Coriolis force, if you remember, is proportional to the cosine theta. And on the equator, this layer becomes not so much important, and so we can manage with them in quite different ways than we manage it in the Ekman number. So this is this difference is due to the fact that the Coriolis force contribution to these layers, which I just show you near the equator, is proportional to cosine theta. It's proportional to the cosine theta. And actually, this, if we consider the equation 3-1, equation 3-1, this equation, or 3-9, oh no, this equation. No, 3-9 is from the previous chapter. Yes, there is no such equation in this chapter. So 3-9 is referring not this equation, but this 3-1 also. Okay, just believe that it's proportional to Coriolis force, because it's difficult now to find out this equation from the previous chapter. So in this cosine, if we consider the equator, at equator, where this theta is equal half of p. Okay, in this case, the latitudinal dependence in the derivatives can no longer be neglected compared to the radius dependence. Before that, we neglected by latitudinal dependence, but near the equator, it becomes about 0, so it plays the same role. To determine the critical criteria for the transition from the Ekman layer to the equatorial shear layer at latitude, here we have polar longitude, but if we consider latitude itself, it's related to this theta like p half minus theta, and in this case it's actually about 0. And this is exactly which is coming out for this value, this small value. Or maybe even better to write down that this relation, we mark it like, let's define it like x, and in our case it's much less than 1. So we are staying in this combined boundary and shear layer. Then from the last two equations, 3-1 and equation 3-2, from these last two equations. Last two equations, there is two equations here, this one and this one, which we didn't use actually, but let's now time to use them. For these two equations, we obtain to balance every magnitude, to balance this, to balance this with this, this with this, and of course at different boundary layers, or the different age of the boundary layers, we obtain balances in order of magnitude. Here I will write down all the balances which we can estimate in order of magnitude. X. Let's write down from last two equation of three B.12. We have balances. The balances are like this. We have, you see that these two last equations starting from V phi, and this V phi is actually appear like X V phi that is proportional Ekman Ekman V theta over delta R squared, then X V theta. Oh, sorry, not B, yeah, just 3.1 and 3.2. Okay, so it's not this system. And then there is a balance between X V theta is proportional to VR. Then the same is proportional E V phi dr delta R squared. I will explain later what does it mean, this delta R squared and everything. Then again we have actually three relations for last two equation in 3.1 and for one equation from 3.2. Delta R squared. Then there is, let's put it like this one, VR delta R is proportional V theta over X, where X is this variable. Okay, this is 3b6 formula. Here, delta R, here delta R is the radial thickness of the equatorial layer, and the first sign and the first balance is obtained from the latitudinal equation 3.1, from the latitudinal equation 3.1, which was in previous chapter, under the condition that the decreasing Coriolis force remains compensated by the radial component of viscosity. You see that there is a trick here that Coriolis is proportional cosine theta, so it's actually proportional to this x, which is half p minus theta. So its Coriolis force become diminishing. And to take into account this, of course, this outside of the equator, this Coriolis force is not so. It's very important, perhaps the most important force in this equation, and it's work. But if we are inside near the equator, then Coriolis force becomes not so important, and it's proportional to this x, which is actually different in the latitude from the equator to some position near the equator again, but slightly far. So here delta is the radial thickness of the equatorial layer. So delta is radial thickness of equatorial layer. Okay, let's abbreviate it. And the first balance is obtained from the latitudinal equation 3.1 under the consideration that the decreasing Coriolis force remains compensated by the radial component of the viscosity. When Coriolis force is proportional to x, or other words, this Coriolis force proportional to theta, or it's the same to x, and when it's vanished at the equator in the left-hand side of the latitudinal equation, the latitudinal pressure gradient remains for the balance. And the second and the third balances in 6, second this and this third balance in the 6, follow through the azimuthal, actually last equation, which was shown in 3.1, in which the derivative of the pressure vanishes because we are considering a flow symmetrical about the rotational axis. When the Coriolis force vanishes at the equator in the left-hand side of the azimuthal equation 3.1, the radial velocity component remains for the balance. Actually, this is balance of the third one. And then we again play the same game. We simply identify transformation from 6, and we obtain this estimation when taking into account all the balances, that x is proportional to Ekman number in 1/5. Then delta, this is the x actually measure this distance. This distance is all the length of all this shear boundary layer, equatorial. But if we consider the next stuff, it is the thickness of the equatorial shear layer, which is actually associated here with x, is e to 1/5. If we consider all the previous balance which I showed. And so, and the width of this layer is of order e to the 2/5, and then the latitudinal velocity, at this case when the Coriolis force is small, is of order azimuthal velocity, and then and the last relation, we can proceed further in this relation, and here we have that the radial velocity in this layer is quite small. Actually, it's work like e to the minus 1/5. It's no wonder because it's quite difficult to overcome the radial direction, and so it should be small. Okay, e to the 1/5. So if we just return to this and estimate VR from Wi-Fi, we see that e to the 1/5 goes this way. So in some sense, the radial velocity is much smaller than the remaining velocity. But the power here is not so big because, for example, for the case of the Earth, this effect will be 10 to minus 2, something like that. So it's not so strong effect like we considered before. Okay, in this case, the value of the radial velocity component is maximum here in accordance with the last relation from 7. This is the 7, 3b, 7, like that. And the equation for determining the flow in the equatorial shear layer are obtained from 7, under all this condition, and the Navier-Stokes equation, so original equation, and incompressibility condition. For the more details, you can see the problem, which will be stated later, problem 2. And the final equation for all these things, we have two types of the stretched variables, and the final equation for all the stuff is following. So some additional to the pressure Okay, so some addition to the pressure could be with xc, whereas xc again it's stretched variable, but not quite different variable from that we used for the Ekman layer. It's rather different. It's working only near the equator here. So this stretched variable in the corresponding direction is related to semi-Coriolis term V phi, the first equation. Second equation is a little bit tricky. It's dq additional to the pressure dx capital. We use next stretched variable instead of the small x. We use in capital X, and this will be stretched variable, which we explained further. Minus 2x y phi and it's equal second derivatives of v theta again dx Okay, then the third equation, very similar one, but I stress that here we have Coriolis force effect, but multiplied it by the stretched variable, which originally comes from here, and later I explain in detail how it's works. Also, there is R variable. It's actually how with the radial component of the velocity. So just use it as like capital R just to distinguish. But it's normalized radial component which will write down further. So this is equal second derivatives of v phi d c in second. And one more equation. I didn't fit it here. Let's fit it there. This equation came from the divergence condition. This first three come from the Navier-Stokes equation. And this one is from the divergence condition. Okay, this constitutes the system 3b8. And now let's explain here the coordinates are used, stretched along the radius and latitude. Along the latitude just to accommodate this e to the 1/2, and along the radius to accommodate this e to the 2/5. So this stretched variable can be written down. Actually, they are related to the same formula, so we will not prescribe another formula for this. And this is xi variable. Of course, it's related to the radial variable, and by definition, it is r minus 1. So it's inside the near the inner cylinder and not inner, out of the inner cylinder. So it's always more than 1. And so it's divided by e to the 2/5. This is stretched variable. And another stretched variable, capital X, is by definition, as already we wrote, p over 2 minus theta divided e to the 1/5. Okay, actually this is the formula with the same number, and the pressure P and the radial component of velocity are expressed through the function Q and R. So actually here we have some funny function like this Q and this R capital. So this function are very simply related to the real pressure, like that. V 2/5 Q and VR, R component of the velocity, is equal e to the 1/5 R capital, which used in this system. So all these things are actually related to this formula. Okay, so we just write them nearby. So after this derivation of this length formula, let's now proceed to the general structure of this flow. And for that we stop here, and then let's discuss this general structure of the flow which we have found. And this flow is named Proudman-Sturgeon flow, and it's now we actually are near the final paragraph of all this course. Not all this course, of course, but all these things which are connected simplest differential rotation. So in this chapter we have discussed qualitatively the structure of the shear layers in the tangent cylinder for the Proudman-Stewardson flow. The larger scale part of this flow was discussed in detail in the previous chapter. The flow in the Ekman boundary layer were discussed in detail not in all detail, but at least in some detail. We didn't solve the system. It's also tricky stuff to solve the system, and but I comment better later about that. And the final Ekman boundary, the final summary of the general structure and the most important detail of this complex flow is summarized in the illustration, in this illustration and the following illustration. But let's start from this illustration. Okay. On this figure which you see here, this figure, first of all illustrates the fact that the rotation of the inner sphere with a slightly higher angular velocity, I just stress that this rotation here is with slightly higher angular velocity than everything is rotated. High angular velocity leads to the transfer of angular momentum and mass, which determines the entire flow under consideration. The relative magnitude of the slightly faster rotation of the inner sphere is determined by Rossby number. We introduced it 2 chapters before that, this Rossby number. Perhaps you remember that it relates the rotation and the relative velocity. And for the Earth, it's 10 to minus 8 or something like that. So quite 10 to minus 6 more precisely. Sorry, I don't remember exact figure, but something like that. So, which is so small that the original equation are linearized. So actually we remove this Rossby number. And we are left only with one parameter. In this case, the entire system rotates so quickly that the only remaining similarity criteria, the Ekman number, can be considered asymptotically small. So actually all the game is around this Ekman number, and we get in different boundary and shear layer, which is dependent on this boundary. As a result, outside the tangent cylinder, which is shown on this figure as well, outside the tangent cylinder, the fluid is in solid state rotation. It was a special figure where we discussed that the outside the tangent cylinder, in terms of the geostrophical flow, the fluid is in the rigid rotation, but inside there is some geostrophic flow. Very simple, monotonic one. That if we consider angular rotational rate, it just monotonically rise from the beginning, from the center of the near the axis of rotation. It's about 1/2. Then it rising up to unity, and on the boundary between on this boundary, it has dramatically higher, even infinite derivatives, and here it's just rotates rigidly with the mantle. And I just remind you that here we have a mantle if we consider this picture in the terms of our native Earth. And its profile determines the balance of the amount of fluid flowing in and out of the outer and inner Ekman layer at the same distance from the rotation axis, and thus the meridional flow in the tangent cylinder is concentrated in narrow Ekman layer, and in the main volume of the tangent cylinder there is only a weak e to the 1/2 axial flow directed from the outer Ekman layer to the inner layer. So there is some general flow, and there is only small contribution from this part where the shear layer and boundary layer are intersected, and here also there is such a structure where we even have special equatorial type shear and boundary layer combined. The return flow of the liquid occurs on a complex shear and equatorial Stewardson layer on the tangent cylinder. So there is a upgoing flow inside the tangent cylinder, and there is a return flow. And all this return flow is important because actually it's working in the shear layer. So we discussed the shear layer. It's very important in the terms that it's produce the return flow, and it has very small scales. So if we consider, for example, for future application of all this picture to the magnetic generation in the planet, we see that the most important gradient are directly on the tangent cylinder. And so we can make the simplified model which catch this feature. And frankly speaking, almost nobody. People just find when they are making their model of the geodynama and planetary dynama and so on, and solar dynama, star dynama, whatever. They of course notice that there is very crucial role of this tangent cylinder and all the shift layers. Stewardson, typical, of course they are not exactly Proudman Stewardson, but very similar. So why to, for example, I'm just saying the idea, why not to investigate this case when we have applying the special numerical procedure just to resolve this layer. So we just have more point here and less point here. And so again here with the more point and less here. So and of course near the boundary should be more point, more concentrated mesh. So actually we numerically could take into account all these features, and so eventually we obtain the flow. So here the sharp discontinuities as angular velocity of rotation are smoothed out, which reach the maximum value on the tangent cylinder and immediately outside the tangent cylinder. And immediately outside the tangent cylinder, it stumps to the zero. In addition, the weak meridional current, which also has sharp discontinuities on tangent cylinder, is smoothed out here. Each of the layers is responsible for smoothing out individual characteristic of the flow. Oh, I jumped. Sorry, I jumped. Okay, sorry, I jumped. Oh. Here the sharp discontinuities and is smoothed out here. Each of the layers is responsible for smoothing out individual characteristic of the flow. And the most important layer is one with thickness e to the 1/3, since the second derivative of the angular velocity of rotation, which is directly related to the energy characteristic of the flow, is smoothed out. And actually you can see the problem which is stating this course for you. And the structure of the boundary shear and equatorial layer becomes clear already at Ekman number about 10 to minus 3. It is especially clear manifested through the lines of constant angular velocity, which are shown in the following figure. This following figure, this one, was direct numerical calculation, the same situation. And you see that even for the Ekman number 10 to minus 3, not that small, like in the where it's 10 to minus 8 or 10 to minus 15, we already have all the structure which we just discussed it with you. And this all the structure appears here. So you see that there is Stewardson layer, which is appear here. It's the actually for angular velocity picture, and here there is almost rigid body rotation. Of course, there are Ekman layer. Here there is the Ekman layer. There is another Ekman layer. There is a tricky equilateral Ekman layer which appears here. Of course, if we proceed further, we have a more clear picture for all these things, and eventually we can outline. But it's nevertheless, if we proceed slightly further, even to 10 to minus 5, this actually will be so thin that it's impossible to see. But of course, we can make this some magnification of some places, and so it could be interesting work to at least illustrate how all these things are working, and also this work could help us to formulate the idea how to do it more properly, everything of that. Okay, so actually we almost finished this part of my lecture course, which is related to some sort of the general hydrodynamics in application to the planetary situation. And on the next lecture, which will be tomorrow, we will start already with convection. So we will all this stuff which is related to the general hydrodynamic is stopped here actually. So, but only because this the last paragraph is the most complicated one. So I can give you sort of the complementary task. If you solve them, then you are a perfect person. And then if you don't solve, no any obligation, you can pass the ordinary exam. And so I don't know, Maria, will be this task available or?
Before that or after the exam, but during the day. I'm talking about first 6 tasks. And these extras, of course, it will be given and discussed later. So, yeah, what I meant that you now have the possibility to ask specific questions on these tasks, on these first 6 tasks, if you got any. Today, we're supposed to submit them. Yeah, let's do it like this. To ask those questions about first 6 tasks and extra tasks.
Okay, but
the discussion of extra tasks is planned for tomorrow. Yeah, some special.
no, when you mean extra task, which is
Yeah.
this chapter,
Yeah.
which related to this shear layer. But I think that this is sort of premium task.
Yeah, but
So maybe we could consider this is quite difficult subject. So maybe we will consider the premium task. The previous task, let's like just all this.
yeah, there's not ordinary, but tomorrow we've got a special tutorial, special tasks for answers.
Those for the and I saw that tomorrow goes as
No, the lecture and tutorial.
So tomorrow, as Maria told you, you can ask me what about this extra task, and if you answer this extra task, you will be premium student or something like that. And as well as I'm able. By the way, I didn't say that. Just let me do some comments. Some comments on the problem skills.
Because actually to answer this task, this Proudman-Stewardson paper is very important because everything is there. You see that even our combination of the sphere, all the spherical shell is. This paper is accessible. Maria, is this paper accessible for the student? Proudman-Stewardson. Okay, so you can easily take this original paper. Everything what we are spoken about is everywhere here, but much more, even much more. So important things to know that here he used not Ekman number, but the inverse Ekman number. So this R is in fact inverse Ekman number. So now it's become not small but larger parameter. But this larger parameter is you have higher order derivatives, which is the second order, and you divide by this larger parameter. So effectively, you have small parameter near higher order derivative. And if we consider how this working, you see there is a statement of the problem. Then he wrote the different notation. Some of the notation are exactly as ours. Omega, for example, he also used. And there is also, of course, quite different rotation. He used for cylindrical radius, he used rho. And for z direction, he used this variable. So there is some difference in notation, but it's not so big. And of course, he operated slightly different manner than we did. He used the flow functions, and so he reduced to just one function, which is written here, or two, and then he manipulates this equation as in a similar way as we did. But there are some difference. For example, he accounts boundary condition like that, not exactly like we. And then he solved this system. Reduce the system to the simplest layer. Then consider the boundary layer, Ekman boundary layer, as we did. And actually, only the up to notation, it's quite similar what we did. Maybe you remember there is a fourth derivative in the stretched variable. Here there is a second derivative in the stretched variable again. And this cosine is the composition Coriolis first term, which is actually neglected here. Not neglected, sorry, so it was used here, so it's quite similar stuff. So then there is also different representation of the function, and he got the solution for this boundary layer near Ekman boundary layer, which is exactly like ours. Of course, there are some difference in notation, but in fact it's the same. And then, he found that there is a solid body rotation. This means in his notation that there is solid body rotation outside the tangent cylinder, and there is a boundary layer condition that there is imposed. He used just two functions, not three as we used. And then he proceeded further. Then he stated the Stewardson layer, how it's work. And for different combination, he started from the equatorial layer, with which we finished, but he started with the equatorial boundary layer, and also wrote the similar equation and proved them in some manner. And then he proceeded even further, and he proceeded to this 1/4, 1/4 and 1/2 boundary layer. Here he got the solution. Okay, see, you see, and this is after considering this Ekman type boundary shear layer, because it's a boundary and shear simultaneously. He proceed to another shear layer. In our term, this is the most important shear layer, which is in our notation e to the 1/3. And here he made the manipulation and managed to find the solution to this problem. Rather simple solution, which is shown here. but then it's complicated, and it even find this value of the flow, which is made full adjustment. I did one Ekman number in 128. It's quite tricky, but nevertheless, from the rigorous asymptotic analysis, it's coming out. So there's additional difficulty which I didn't load you. And also, but if you like, you can understand how it works. And there is also the inner layer. In our notation, we call it innermost boundary layer. And here he made some expansion, again got the precise asymptotic solution. And then he proceed further, as we did, maybe you remember that we were taking the integral just to have the acceleration for the function. See, he is doing similar things. And proceed further, but there is some things that we didn't do, because maybe they are in terms of the value not so important, but in terms to match all the asymptotic together, of course they are important, and there are quite tricky stuff like this 112, 112, 21 power, very complicated. And so eventually he found almost exact solution for all part of this problem. You can just see them and understand. And this is quite interesting stuff. And again, I should mention that in fact all this stuff is at that time it was 1966. At that time it was no computer technique. And all this nice, all this beautiful stuff which Stevenson found, you see that he found everything, all the function, all the matches, all everything. So he expressed all the which available in a very detail, and actually in asymptotic semi-algebraic form. So it's a big advance. It could be maybe quite interesting to repeat it on the computer and to compare this asymptotic solution and computer solution. So maybe if you succeed to understand this article, you could regard you as a true scientist. So my suggestion is just to go through, because actually there are plenty of ideas how to work in different difficult situations, shear, boundary layer, and of course eventually with the turbulent stuff and so on, which is perhaps it's one of the most advanced work till now time. So in this ancient time, people were quite clever. Okay, so maybe there is no, it's okay. There is, you see that not so big reference list. People at that time made very original things and very clear stuff. Okay, so maybe there is some question to all this heavily interested part. But anyhow, you can think a bit, and maybe tomorrow when you, Maria, excuse me, will be this task available on the net that they should understand what to ask? Yeah. Okay, everything will be available to you. You just see, and if you find some question for me, you please welcome tomorrow, and you say that. And tomorrow, hopefully, we will proceed further to the convection. Maybe it's more realistic stuff. This, of course, some sort of of course, it's classical problem, very classical problem, very deeply founded, and it's very fun of the science. But nevertheless, it's not so practical. But it's an interesting situation that very often not so practical problem solution becomes very, very strongly available. So we hope so. So one day this Stewart's law will be available and help us to understand the very essence of the science. because it's rather tricky stuff and complicated and interesting from my point of view. Frankly speaking, even some places I didn't understand. Okay, maybe if there is no question, then it's one. Okay, so we finish, yeah? Okay, thank you for your attention. Yeah, you can prepare the task. The question about this task you can ask me. And perhaps if you perform this extra task, at least just some of them not so difficult, but it will manifest that you understand. Okay, we can stop, please.
The papers are here. Write your name, okay, and submit. The date also. Okay. So by tomorrow, today evening also can submit. So but discuss here. That's what I want to do. If you discuss among yourself, it will be easy for you to do the task. Isn't it? Now that is one thing. Another one is 2:30 you are going to write the exam. It's multiple choice only. And some whatever we have discussed, some problems. On tutorial class, Maria Madam has discussed those things are asked there. You have to write down. So 12 to 13 questions we have to write. 4 questions you have to deliver. Okay, so 2:30 you can come here. We will start the exam. That is one thing. Another one thing is you are doing the code in the lab. That code also you write down. Okay, the title, diffusion equation, and some steps how you are discretizing. That one and the code. You submit that. These are the 3 different tasks I did for you. Apart from that, one more thing I want to let you know is tomorrow and day after tomorrow we have some time. Each one of you, I will split you. Give 5 to how much time you want. Okay, some presentation about the topics. If it is a derivation also, you can come and do one derivation. Is it okay? Is it okay? The PPTs are with you. Somewhere we have to do the derivations, no? So that derivations,
I checked last 6.
yeah. So that is Tuesday and Wednesday. Thursday we will go for another. Lastly, she should do spectral analysis. No? That one we do. Okay? That code we do. Outline of that one I will give you. For the linear one, non-linear one later we will do. Same equations, whatever we are taking up there in the finite one. That equations we will do. So these are the another 4 days work. So we are going to sit here only and we will do the work. So what we are so tense. Okay, there is nothing to be tense. Extra task. Okay, sit and discuss yourself. Whoever is to run that work, you can pass it on to others also because it is a published work. That's what sir has done. You can do. Okay. Now sit and do that WhatsApp one, whatever task we have shared. Last 6. Okay. So these are the tasks given to you. You sit and do up to 1 p.m. here. Then you go for lunch and come back by 2:30 as usual. Okay.